Hi students. Last time we saw that if we apply an input signal to the non-inverting input of the op-amp, that the output on the other side will have the same sign as the input. So now let's see what happens when we apply a voltage to the inverting input. So if we have an op-amp here, we have the non-inverting input here and the inverting input here. It might be an upside down orientation. So this time, let's take this non-inverting input and let's tie this directly to our ground line down here. And then let's take at the inverting input, suppose we have an input resistor here, and let's give this an input voltage, and I'll call this V in. Okay, so our output is going to be over here. We're going to have some terminals here across which we will measure our V out. And then remember that like 99% of the op-amp circuits are going to have a negative feedback loop. So we're going to have a negative feedback loop here. The resistor that's in the feedback loop is called the feedback resistor, so I'll label it R sub F. Okay, great. So then suppose I call this my input A and my input B. Now, if you remember the way the op-amp works is it's going to amplify the difference between A and B. So if there's a voltage difference, let's call this VB minus VA, this is a thing that's going to get multiplied, right? So amplified by a gain of A to give us our output here, V out. So that means that if one of these is tied to ground, VB is actually going to be equal to 0. So the voltage difference between VA and VB is just going to be, so VD, the difference between them, VB minus VA. Since VB is 0, this is 0 minus VA. So it turns out that this implies that negative VA is what gets amplified. And that's why we call this an inverting circuit, because it's going to invert the sign of our voltage input to this inverting input here, and that's what's going to give us our output. Okay, great. So we're going to do circuit analysis on this example. We get to use the ideal op-amp approximations. And those are, we have that VA is equal to VB, and we can say that IA is equal to IB is equal to 0. And recall that we get to make this approximation here because in order to stay in the linear amplification region for this op-amp, we have to have that the difference between VB and VA has to be less than or equal to VCC over the gain. So VCC, if you remember, is going to be the power supply that turns the op-amp on. So plus VCC here and minus VCC here. You don't always see this in the schematics because it's not really a part of the circuit. This is just where we turn on this op-amp. Anyway, so that's where this approximation comes from. We get to make this approximation because our Rin is so large. And by Rin, I mean the internal resistor that goes between A and B. I'm going to label this R1 so that's not confusing. This is, it is an input resistor, but it's external to the op-amp, so I'll label this as R1. And remember, Rin is the resistor that goes in between these two. And because it's so large, we say, oh, it's practically infinity, so this looks like an open circuit, therefore we're going to have no current that comes in here. So if we continue with our circuit analysis, if we have a current that originates from this Vin and takes a path through R1, let me label this I1, and then we've got this circuit that the current that comes in here, which you guys know is actually 0 because of our ideal op-amp approximations, but just for the sake of an accurate KCL equation, I'll go ahead and put it in there, and this is IF. Okay, great. So then if I'm going to do a node voltage analysis to solve this circuit. So at this node here, I'll call this the VA node. So at node V sub A, we have by KCL that I1 is entering the node and IA plus IF are going out. Okay, but we know from the ideal op-amp approximation that this is actually 0, so our equation is I1 is equal to IF. And now at this point, I'm going to replace my currents with an equation in terms of V over R, right? So I'm just using Ohm's law there. So to replace I1, this is going to be the voltage difference between this voltage and that voltage divided by the resistor between. All right, so the voltage on the left side is V in, and then on the right is VA, and I'm going to divide that by R1. And then I'm going to replace this IF with the voltage at this node minus the voltage at this node divided by the resistor in between. So this is going to be VA minus V out over the feedback resistor. Okay, so then what do we get to say? Well, we know that because of the ideal op-amp approximation that VA is equal to VB, right? And we also see in our circuit here that VB is tied directly to ground. So that means VB is equal to 0. So this implies that VA is also equal to 0. So wherever I have a VA in this equation here, I get to just replace it with 0. So now my equation is V in over R1 is equal to negative V out over RF. Now I want to write an equation for V out in terms of V in, and that is going to be, I'm going to have a V out on one side and everything else over on the other side, negative V in times the feedback resistor divided by the input resistor R1. Okay, so what is this telling us? This tells us that our output after the amplification is a function of our input times this constant right here. So that means that if I wrote it like this, here's my V in times some constant, this is negative RF over R1, that this thing right here is our gain. So if you are asked to design a circuit that is going to invert your signal, right, or flip it upside down, and you want a particular gain, say like 3 or something like that, then you just need to pick RF and R1 such that the ratio between these two is equal to 3. So in the next video, I'll show you another example, a slightly more complicated example of an inverting amplifier. So let me know if you have any questions.